Thanks a lot. I appreciate the invitation. It's always a privilege to speak here at the IAS. I'll be talking about some work that I carried out with my current student, Mehmet Demirtas, my former student, Cody Long, now a postdoc at Northeastern, and my colleague, Mike Stillman, who's a mathematician. This work appeared over the summer, but we've been building up related things for some time, and we have forthcoming work also that I may mention a few things about. The main idea is that we explore a class of string compactifications with many moduli. I'll explain why we pursue that. And to achieve this, we develop new methods for analyzing the topological data of Calabi-Yau hypersurfaces in toric varieties. What we find is that where the alpha prime expansion is under control, in a sense that I'll make precise, there are large cycles and many ultralight axions. So the plan, I'll briefly motivate studying constraints on quantum gravity. I'll then spend a little while describing our strategy for approaching an enumeration of solutions of string theory and explain what possible applications of this program of work are. I'll then describe one main computation studying the Kreuzer-Skarke database at large H11, and I'll indicate our results. And then if there's extra time at the end, I may say a few words about non-BPS instantons in this same context. So first, quantum gravity motivation. Our goal in this work is to understand the consequences of the UV completion of gravity for observable phenomena. And of course, for most observables, quantum gravity decouples, and it's perfectly safe to be agnostic about what the ultraviolet completion is. But there are some fundamental problems that do depend on quantum gravity, most famously large field inflation. More generally, the question of the existence of certain EFTs, the landscape swampland division. And these problems provide us with really exciting opportunities to test and to use our ideas about quantum gravity. So that's the broad motivation for this kind of work. So many people are now engaged in a rapidly advancing research program that seeks to determine which four-dimensional effective field theories arise as long wavelength limits of consistent quantum gravity theories. The first method for carrying out that kind of work is to use consistency arguments, drawn on things like black hole thermodynamics, important principles like causality and unitarity, reasoning from holography, and the like. And this principled approach was, for a long time, the main driver of developments in this subject. But in recent times, a new and easier method has emerged, which is just to conjecture without much constraint on what the conjectures are. And that's not the only thing you could do. There's a third way. And the third way is to enumerate EFTs in vacua of string theory, namely to study for the EFTs that arise from weakly coupled quantum gravity theories where you can do computations. So if you could do that, and we'll give some steps toward that, there are a bunch of things you could apply it to. You could use an enumeration of vacua of string theory to try to understand moduli potentials, moduli stabilization, the resulting cosmology. You could also use this kind of enumeration as a way to winnow these sorts of conjectures, as a test for conjectures that are perhaps too strong, or as a way of supporting ones that may be on target. You can use these sorts of methods to find the boundary between the landscape and the swampland, which, if you've read today's archive, is now named the marshland. So that's we're seeking to define this boundary right there. And if you haven't read that paper, you have to read the marshland paper. Now, a further goal, which goes beyond trying to determine which 4D EFTs arise in quantum gravity, seeks to characterize the distribution of EFTs and attempts to characterize what constitutes a typical such EFT. In other words, it's an attempt to count solutions of string theory by different properties that they have. So this is in the spirit of old work of Douglas and Zenef and Douglas, among others. Now, since this is the slightly more atypical application of the work I'm describing, this is, I think, more mainstream in the present era. Let me briefly describe why we would want to count solutions. What do you plan to do with that? Suppose string theory has some large but finite number n of isolated solutions, so solutions with a mass gap, that fulfill some set of criteria, C. maybe 3 large dimensions, standard model gauge group, you pick whatever else you like. You could say a suitable inflaton candidate, an Accion for QCD, whatever else you want. Now, if it's also true that an overwhelming fraction of these solutions that fulfill the criteria C that you've chosen also have some other property P that you didn't dial in, then let's imagine, say, light scalars and pseudoscalars. I'm just making up an example, it could be anything. Some property. Then a reasonable null hypothesis is that P should also hold in our universe. Now, it's really just a starting point null hypothesis, and the reason for that is that this is a counting measure prediction in the sense that I'm excluding dynamical selection effects of the sort we would expect to occur in eternal inflation. I am, by construction, omitting them. That means that I shouldn't take predictions from this approach to be definite final answers, but some starting point for thinking about which things occur frequently and infrequently in string theory. Now, if we use this counting measure approach and we predict some property P that's then observed, well, fantastic. That's, of course, a successful prediction. I don't have a tremendous amount of hope that that will actually work out, but observing not P would also be interesting, because that would tell us that our universe either involves some fine-tuning or dynamical selection, or else it's just not described by solutions of string theory that obey the chosen criteria.
Right. C includes the standard model gauge group, the 3 generation, and the proton that hasn't decayed yet.
Yeah.
Is n not equal to 0?
I don't know.
Isn't that a bigger problem?
The hard problem in this setting is picking criteria that are usably restrictive, right? And so the art would be to pick some set of criteria that don't lead to the empty set, but that lead to a set of solutions among which that are so large in number that they have undiscovered properties P, P prime, P double prime. And the reason that I'm describing this in this sense is I want to make it clear that I am aware of the problem of choosing the criteria and the problem of selection effects, but I'm separating them out for now. Okay, so we're just counting things, and we can only go so far with that. Now, but why would we try? Well, the idea is that when n is really large, some properties P are just overwhelmingly dominant at the level of counting. So unless there is multiplication by 0 somewhere, then we ought to ascribe some force to this null hypothesis. And we'll find some evidence of this due to just the combinatorial or exponential growth of the number of solutions in certain classes. This is by far the most preliminary part of the work that I'm describing, the partial evidence for this, but this is the spirit underlying the search for large numbers in this setting. So the hope is just the dominance of some properties P is strong enough to furnish useful initial predictions, even without a theory of selection, which seems far out of at least our reach. Okay, but if this is going to work, if any of this is going to work, whether the counting or just the testing of quantum gravity conjectures, we need a large ensemble of explicit solutions. So how do we do that? We're going to work with Calabi-Yau hypersurfaces in toric varieties. Finding Ritchie flat 6 manifolds in the wild is hard. And in the case of Calabi-Yau threefolds that are hypersurfaces in 4-dimensional toric varieties, the problem is combinatorial. And that makes it easy to automate. That's the key advantage we're going to use. We're going to use that to build a pretty large ensemble, millions at present, but we could easily get to as many as we have storage for, of geometries and their EFTs. And this could serve as the foundation, as I was implying in the previous discussion, for searches for quantum gravity constraints, de Sitter vacua, inflationary solutions, and the like. And I should advertise at the outset that although this is going to be a really large-scale computerized search, and so transcends many of the limitations of pen and paper searches, these examples can all be checked by hand. At most levels of the examples can be checked. So once you know the one you really want to focus on, you can go back to it and do most of the steps by hand. So that's sort of nice. Okay, so what's a toric variety? It's an algebraic variety that can be assembled by gluing together algebraic tori, which is to say powers of C star, according to some instructions encoded in a lattice polytope. A lattice polytope is just the convex hull of a set of points in a lattice. Here you should understand C star to the 0 as a point. So for example, CP1 is constructed as C star, union the point that's the origin, union the point at infinity, thus making the Riemann sphere. And then you just do a grander and grander version of this with more and more copies of algebraic tori of different dimensions. The point is that the instructions are encoded in a simple combinatorial object. And there's a large class of toric varieties encoded in particular 4-dimensional polytopes, reflexive, so they obey, the polytopes and their duals obey some simple condition. And these polytopes have been classified. Now, in 2 dimensions, it's easy to classify reflexive polytopes. 2D reflexive polytopes are these. There are 16. And in 4D, it was a hard piece of work that was achieved by Kreuzer and Skarke. There are 473,800,776. And this isn't just a count. They enumerated them. They found them. They can tell you what each one is. So to each of those toric varieties, if you find a nice triangulation, so-called fine regular star triangulation, I'll define that on the next slide. If you find a nice enough triangulation of such a polytope that yields a toric variety, in which the generic anticanonical hypersurface is a smooth Calabi-Yau threefold.
Is this reflexive condition that the origin is contained in both the polytope and its dual?
That's precisely the condition. Exactly. That it's the unique lattice point with that property. Yeah. Exactly. Good. So what is a triangulation of a polytope? It's a division of a polytope into simplices. So for example, the square is a polytope and can be divided into simplices in 2 different ways. This is where the combinatorial piece enters because you have a choice about how you're going to do it. And fine, regular, and star, these just mean some fairly simple things. A fine triangulation uses all the points. Star, all the points are connected to the origin. And regular means that you can achieve it from a triangulation of a 1 higher dimensional object. Fine and star are easy to check. Regular is a little bit annoying to check, but one can do it on a computer. OK, so this is sort of the reduction in effort. Rather than trying to solve the Monge-Ampere equation, or rather than trying to work with polynomials, we're really just working with vectors in z to the n. And that's finally something that I'm comfortable coding up. OK, so now let's switch gears and describe the notation for the physics that we'll talk about. So I'm going to focus on compactifications of type 2b string theory on orientifolds of Calabi-Yau threefolds. So we just need the notation, it turns out, for the Kähler moduli sector. I runs from 1 up to h11. T is a complexified Kähler modulus. Di are a basis of divisors, so 4 cycles. And then this J is the Kähler form. So this is just the volume of the 4 cycle. And C4 is the Roman 4 form. And so we see that the complexified Kähler modulus has a real part, which is a 4 cycle volume, and an imaginary part that's an RR axion. The Kähler potential for this theory is -2 log of the threefold volume, where the threefold volume is given in terms of little t is a 2 cycle volume. And these are the intersection numbers. And the 4 cycle volumes and 2 cycle volumes are related by the equation on the right. So what this tells us is that if we know the purely topological data of the intersection numbers, then we know the Kähler potential, we know the Kähler coordinates, and so we know the metric on moduli space. And at least at the classical level, at leading order in alpha prime n and G string, where in business we know something about the Kähler moduli space of this theory. Now, a few remarks about the structure of the theory. The axion shift symmetry combined with holomorphy prevents T itself from appearing in the superpotential to any order in perturbation theory. And so the Kähler potential, in general, is the one I've written above, plus a collection of perturbative corrections in alpha prime and G string, which we have no hope of computing, at least beyond leading order, plus non-perturbative corrections, which are in principle even harder, whereas the superpotential has the Gukov-Vafa-Witten form at the classical level, plus a collection of non-perturbative terms. Note that the non-perturbative part is the first place, both in K and in W, where axions get a potential. That'll be really important in what remains. Although I'm ignorant of perturbative corrections to the Kähler potential, they don't provide axion masses. So it's hard to fully characterize the perturbative corrections to K, or the non-perturbative ones, but the non-perturbative superpotential is in some ways accessible just thanks to holomorphy. And in presently understood vacua of 2B and F theory, these non-perturbative terms play a leading role in stabilizing the Kähler moduli and producing potentials for axions. And so what's happening here is we're zeroing in on the information that we can obtain. That is the information of the non-perturbative superpotential and the intersection numbers. Those will be the key objects in the remainder. Any questions? OK. So the computational task, pick a 4-dimensional polytope, find a fine regular star triangulation. That gives you a toric variety. And then you need to compute the intersection numbers of the Calabi-Yau hypersurface inside it. There exist sort of, in principle, algorithms for doing this. But let's see how hard is this going to be. And first, so if you've done that, what have you got? You've got the metric and Kähler moduli space at leading order in alpha prime in G string. If you wanted to compute the non-perturbative superpotential, you've got to start thinking about the topological data not of X, but of divisors in X. We've spent a lot of our time doing that, but I won't tell you anything about it during this talk unless there are questions. That's a separate issue. We have made some progress, but work remains to be done. So how hard is this really to triangulate a polytope? I mean, it depends on how many points there are in the polytope, right? So the number of relevant points turns out to be h11 of x plus 4, in a especially nice kind of case called favorable. And a priori, the number of non-vanishing intersection numbers could be as big as h11 cubed. It's not, as a spoiler, but it could be that big. And in the Kreuzer-Skarke list, h11 ranges up to 491. So, this really doesn't sound that hard. It isn't. To find a triangulation of a polytope with 491 points, you can almost do it by hand. And it's only in 4 dimensions. The problem is fine, regular, and star. If you take off-the-shelf software packages that are made to manipulate toric varieties and made to manipulate polytopes, things like Sage with Topcom built in, and you try and do this, it fails at h11 of about 4 to 8. Okay, so let's see what the arena is that we're dealing with. What I show here is the famous shield plot. Each point is a pair h11, h21. I've put h11 on this angle axis and h21 there. So each one is a Hodge pair. There are 30,000 of them for the 473 million polytopes. Now, easiest ones are the ones with the fewest points, so h11 small, and then as h11 gets bigger, it gets harder. Now, there have been many systematic studies in this very thin band here with h11 up to 6, but those ended up needing hundreds of thousands of hours of computer time. So basically, one needed access to a supercomputer to really do this, and this was up to h11 of 6. Then there were a few scattered studies limited up to 20. And so what we've eventually achieved is we can do the whole thing on a laptop not the whole thing in seconds, but any one of these in seconds, if it's the hardest possible one, to milliseconds down here. And we can reproduce the earlier works up to h11 of 6 overnight on a laptop. So these advances don't come from tweaking memory management or something like that. They come from thinking about underlying geometric constraints that allow profoundly simpler algorithms. I won't tell you anything about the algorithms unless anyone's curious. There are just a couple of places where you have to do computations. You have to find star regular triangulations efficiently. You have to find intersection numbers efficiently. And ultimately find the topological data of divisors efficiently. Each of those was a separate piece of work, but we've been doing it for a while, and we put them all together, and now we can just do this. So what I'll tell you about today is not how one does this, but what the results are, now that we can finally open the box and ask what are the properties of the threefolds up here. Okay. But it's worth taking a few minutes still to ask what we're losing by focusing in on this in favor of, on this rather than on other things. And we should also be asking right at the beginning, if he says you can find a triangulation up here in seconds, very nice, but how many triangulations are there per polytope? I can certainly find one triangulation for every one of the polytopes in the Kreuzer-Skarke list in a year, say. If I wanted to, we could do that. But the problem is the number per polytope grows exponentially.
Can you remind us?
Yes, please.
Different triangulations give you different what?
It's not properly understood. Each different a different triangulation gives you a different toric variety. If the only difference between the first toric variety and the second one is flopping a curve that doesn't intersect the hypersurface x, then that makes no difference for x, although it may affect how you represent x. On the other hand, some of the changes that you make actually materially affect the intersection numbers of x. This is sort of next on the list, figuring out which of these triangulations that result are inequivalent. On a case-by-case basis, it can be done. When h11 is small, it can be done. There's no general theory of it, at least not known to me, and certainly not implemented in general. Okay, so yeah, that's something we've got to do. It'll become immediately clear, actually, on this slide why we are going to have to deal with those degeneracies. So in fact, we were able to prove an upper bound, unfortunately, on the number of triangulations, fine star regular triangulations of a given polytope, whose volume, it's a shape, right, has some volume, is V, and it's this binomial coefficient. So here's a plot. Here's H11 up to 491. This is all the polytopes that there are in the database with these large Hodge numbers. And this is log base 10. So this is 10 to the 900, okay, up here. In particular, for the largest single one, this dot here, which has H11 equals 491, you get 14,000 choose 500, and that's 10 to the 928. The runner-up is 10 to the 65 down. That's this next dot. And this is the first inkling of potentially a concentration of large numbers in one place rather than another place in this set of data. However, it's not solid evidence because I haven't shown you whether the number of these that are inequivalent is comparable to the number of those that are inequivalent. It's amusing to remark, or at least it entertains me, that we improved by 9,000 orders of magnitude on the previous best estimate of this number, which was 10 to the 10,000. But who knows how much further down it's going to go as we start to study inequivalent ones. Okay, I would like to impress upon you that this largest polytope is actually a very friendly polytope. It's a simplex in 4 dimensions. Namely, the locations of its vertices are given by these 5 columns. So it just has 5 vertices at those locations in z to the 4. And here's a triangulation of it, of one of its 2 faces. I mean, it's some nice, reasonable, understandable object. So it'd be very nice indeed if almost all of the triangulations in the database arose on this fellow. But I have no real evidence of that at this point.
What does the minus sign mean?
We could shift everything by +1s. It's relative to some chosen origin. Yeah, so it is translationally invariant, but there's a convenient choice of the origin such that this has the property that came up in Nima's question, which is that the origin is the unique interior lattice point. So this is in z to the 4th, but shifted so it contains the origin. Yeah. So not very many exotic numbers coming in here, but the number of triangulations that result could be pretty big. Now, okay. Integer triangulations, meaning that, well, all I'm doing is connecting integer lattice points to other integer lattice points. Yes, absolutely, only that. Yeah, that's right. Okay, so briefly, just to summarize the choices that we've made, we could have studied more general solutions of string theory, non-geometric ones. We could have tried to study non-vacuum solutions, more general solutions that are Ricci flat but have holonomy that's, say, SO6. And we've zeroed in on, choose geometric, choose Ricci flat, choose reduced holonomy, and in fact, choose a hypersurface in a toric variety. We could have chosen other Calabi-Yau threefolds. And finally, we could, I won't today, but we could in future, for example, zero in on just this one polytope that seems to have so many triangulations. I should remark in this context, this zeroing in is partially inspired by a very early stage conjecture due to Waddy-Taylor, which results from the following observations. First of all, if you ask for all known Hodge numbers attested in threefolds that are bigger than 240, every one of them can be realized in a threefold that's an elliptic fibration over some base. And also, every one of them arises in the Kreuzer-Skarke list. So every Hodge pair, H11, H21, with either of the numbers bigger than 240, shows up both in the list of elliptic fibrations and in Kreuzer-Skarke. Now, the reason that's interesting is that Mark Gross long ago classified elliptic threefolds up to birational equivalence, and they're classified, they're finite. And so you might guess, this is what Waddy is sort of implying, maybe all large Hodge number threefolds are in the Kreuzer-Skarke list. So it might be that this is not just a pleasantly constrained sandbox, but an interesting arena that has most of a certain kind of thing. Okay, so what we'd like to do is develop statistical models of particularly interesting properties of EFTs, because we're not going to be able to enumerate all of the solutions in this class. So what are we going to get? We want to get patterns. And what we'd like to do is work at large H11, find some millions of geometries, and find empirical scaling laws with H11, and use those to somehow understand the structure that's arising in this set of EFTs. In particular, we'd like to think of 1 over H11 as a small parameter in the model, in the spirit of finding a random matrix model at large n. So H11 would be n. I can just remark in passing, in years past, I've attempted to find random matrix model descriptions of structures arising in supergravity. These are pictures of eigenvalue, histograms of eigenvalues of various constituents of the Hessian matrix in supergravity. And this is showing that, for example, the Hessian in supergravity can be written as a sum of Wigner matrix from the Gaussian orthogonal ensemble into Wishart matrices. The connection, the reason I'm mentioning this work now is today's talk is describing a sort of counterpoint to this work. These are, in a sense, spherical cow kind of models of the structures that could arise in low-energy EFTs. And what we'd like to do is refine and extend them by putting in real Calabi-Yau threefold data. So somehow, with enough data, we should be able to come up with much richer models than these that can encode in an efficient manner the relevant structures. Because after all, just a list of properties is of no use. You want somehow a theory of those properties. OK, now, key limitation, which will underpin everything. The topological data in the Kreuzer-Skarke list determines the EFT, or aspects of the EFT, only in the regime of weak coupling and large volume. We'd, of course, love to learn about things in other regimes, but we have to start somewhere, and I won't go anywhere else today. Everything is going to rely on requiring control of the curvature expansion. So now, finally, the results. And the key players in the results are the Kähler cone and the Morricone. OK, so the Kähler cone is the set of cohomology classes of Kähler forms. And the Morricone is the cone of effective curves, i.e. curves realized as one-dimensional subvarieties, holomorphic curves. These cones are dual in the sense that the Kähler cone is precisely the set of Kähler of things J such that if you integrate them over any curve in the Morricone, you get something non-negative. So that's a pairing between these two cones. Now, if we suppose that the Morricone has some generators, CA, where A runs from 1 up to some number P, that'll be at least H11. In general, will be a little bigger. Then, if I were to impose, suppose I impose the condition on J that the integral over CA of J is at least some number, 2 pi squared alpha prime times some number lambda. If I did that, then I would know that the worldsheet instanton action for a string wrapping the curve CA would be at least 2 pi lambda. I might want to do that because I might want to ensure that worldsheet instantons are under control. And so this motivates a key definition for this work. First of all, I'm going to set the string length to 1 in this way. I'm going to define the stretched Kähler cone to be the set of Kähler forms with the property that the integral of that Kähler form over any curve in the Morricone is at least 1, not just at least 0. In other words, I'm preventing any curve from getting too small. In pictures, it's actually very simple. Here are the black lines are 2 generators of the Kähler cone. And because the Morricone and Kähler cones are dual, the Morricone generators are normal to them. And this Morricone generator tells you about a curve that's at 0 volume here and is getting bigger, bigger, and finally gets up to size 1 there. The stretched Kähler cone is the pink region that's far enough away from all the walls. That's going to be crucial for all of our constraints. Now, the logic here is that it's awfully hard to compute perturbative corrections in the alpha prime expansion, but it's not super hard to compute the volumes of effective holomorphic curves, and that's what we're actually going to use. So we're going to use this as a proxy for control of the alpha prime expansion, and at the end we'll have to come back and reflect on whether this is too strong a condition to impose. But it's the one that I'll impose in this work. Okay, now a key observation, the key observation about our data, is a very stupid thing. When H11 is a large number, this condition that every curve has volume at least 1 turns out, for reasons that I'll show you, to imply that some curves and some divisors are very big indeed. That happens as follows. We need briefly to pick a basis and set some notation. So suppose omega I is a basis of 2 cycles, and Ti are their volumes. So the integral of J over some 2 cycle is the associated Kähler parameter. Well, then since these things are a basis, I can write any of the curves in the Morricone as a matrix of coefficients, MIA. These are just numbers, not necessarily positive numbers, just numbers, times these 2 cycles. If I do that, the condition that I'm in the stretched Kähler cone is a set of linear inequalities on the Kähler parameters with coefficients, the elements of this matrix. So just to take a concrete example, suppose we're studying a case where where H11 is 2, but there are 3 generators, omega 1, omega 2, and omega 1 minus 10 omega 2. In this case, the 3 stretching conditions read T1 is at least 1, T2 is at least 1, and T1 minus 10 T2 is at least 1, which is trivially solved, and it's not solved by T1 equals T2 equals 1. The minimal solution is T1 equals 11, T2 equals 1. Okay. That's just saying that once you see negative numbers appear in additional relationships, then to fulfill a collection of linear inequalities, where you have more inequalities than variables, you're not going to be able to saturate all of them. Some of them are going to be substantially undersaturated. That's all that's happening. Okay. Now, it turns out that exactly this sort of phenomenon arises in our setting, that there are more linear inequalities than there are variables, and the solution has to be substantially undersaturating some of them. So concretely, and in pictures, if you have a Kähler cone that's pretty wide, then the stretching moves the apex of the stretched Kähler cone out to some reasonable place. But if the cone is more narrow, then you can see that the apex moves forward a lot more. You should interpret this as meaning that the Kähler form J is really far from the origin, which means the Kähler form is big, which means some cycles are going to be big. That's the key phenomenon. Okay, so just as a concrete example, so this comes from a real geometry with H11 equals 5. So here's 5, 1, 2, 3, 5 across. And then this is like 18 or something, is the number of generators of the Morricone in that geometry. So this is the I index and the A index. And these inequalities can be solved. And the minimal solution makes the divisors have volumes 3, 5, and up to about 5,700. So in this case, where H11 is really not that big, we find some super big divisors. That's going to be relevant because instanton actions will be 2 pi times those volumes. Yes, please. Yes.
The columns correspond to H11?
This is the matrix of coefficients of the Morricone generators in a chosen basis. So let me show you this here. So here I've picked a basis, fix 1, and this is a matrix such that a curve C1, say, is M1I omega I, so this just gives the coefficients. Each row of this matrix is one of the curve generators. So here, this is the first curve. It's minus 3 omega 1 plus omega 3 plus omega 5, et cetera.
So H11 is 5, but there are 25 generators.
Yeah, or 18 or something. Yeah, something, exactly. Right. And so each one of these is a condition. So this condition says that minus 3t1 plus t3 plus t5 has to be at least some number lambda. This says t1 minus 2t5 is at least lambda, et cetera. So just a whole bunch of very simple linear inequalities, but notably that include some negative numbers. Now, to be honest, we didn't know how many negative numbers were going to show up here before we opened the box. You could have imagined that there would be some theory that somehow says that the Morricones are nice in a certain way, and in some natural basis, they don't look very negative. Well, it's just not true.
As you make that integral of J bigger and bigger,
Yeah.
I mean, clearly parametrically, if you make it really big, your effective cone eventually turns into a cone over a simplex, right? I mean, in other words, the number of relevant walls is just equal to the dimension of the space. Instead of losing them, you don't lose all of them, but as you say, like many.
You can focus on some of them when you're far out enough. Yeah.
But do you know? I mean, it's an invariant question. Instead of choosing 1, that number 1 for the integral of J to be 1, it's an invariant question. How big you have to make it before it does collapse to a cone over a simplex? Do you know the answer to that question?
No. Let me think if I can give partial answers. Well, at a very modest distance, it becomes a cone over a polytope that's not a simplex. But then further out, it may simplify further.
Yeah, it must. I mean, if you do nothing, it's just a cone over. Well, it's a cone over some polytope, and as you make J bigger and bigger, the polytope gets simpler and simpler. It has fewer and fewer facets, right?
Well, it's still. I mean, the structure of the Kähler cone itself is still precisely a cone, but you're saying that there's an approximate sense in which we can ignore some of the facets, right?
Well, I'm just saying that what you're saying is that you don't in everything which satisfies your integral J bigger than lambda, there are some of the inequalities that are not saturated.
Yeah. Yeah.
So we just focus on,
yeah.
so in other words, as we make J bigger and bigger, we get to throw out some of the inequalities.
Right.
And so, well, presumably it happens in some discrete way, right? If we say the integral of J is 10 to the minus a million, then all the inequalities are still presumably saturated somewhere. And as you make it bigger and bigger, the number of things that can be saturated drops until eventually, presumably, you're just left with the minimum number of inequalities to cut out the space. I'm just asking the question whether there's some sense in which you can see what this shape looks like as you increase the integral of J.
I can't give a precise answer to that now, but what I will show later is how these divisor volumes look once you've sort of entered that asymptotic regime where we are paying attention to the ones that matter. And it would be nice to come up with a more tomographic view, but I don't have that now. Yeah. Good. Other questions? Okay, so results. We find narrow cones, and those give rise to large cycles. So first of all, the walls of the Kähler cone turn out in our ensemble. So we studied 2 million geometries with H1 up to 100, and then some also up to 491. The walls of the Kähler cone are nearly parallel. I mean that in the following sense. If you consider all the walls of the Kähler cone and find the pair that's closest to being back to each other, that's what I'll call that angle theta min. We find that cosine theta min, as H11 gets big, becomes almost -1. So there exist some nearly parallel walls of the cone. Not to say that many of them are like that, but at least some pairs are like that. All right, well, that causes this sort of scissoring phenomenon in which the apex of the stretched Kähler cone moves very far out from the origin. Next, we find the stretched Kähler cone is far from the origin, so I'll use d min to describe this distance. And in this swordfish picture, you can see how big it is. Here's 491 there, and this is the log base 10 of that distance. And you see it goes out to roughly 10 to the 5 or something like that. Okay, so that's the distance d min. As a general remark, this is not one of our key results, but it's amusing to note, the intersection forms are quite sparse. Instead of order H11 cubed entries, there are just order a few times H11. So this counts the number of non-zero elements of the intersection form versus H11. Not that many.
So
yes, please.
The distance is telling us about the volume of the Claviau, the minimum volume of the Claviau inside the stretch.
Yeah. Not directly. I'll show you that in a few minutes. And in a moment, I'll show you V itself. But this is somehow an easily computable proxy. This is the only easy to compute proxy for the volume. When you want to compute the actual volume, you have to do a minimization inside the Kähler cone. So that's where my students suffered extensively in performing real minimizations. Whereas some of these problems you can do by linear programming. And so we sort of, to the extent possible, zero in on the linearly programmable ones when H11 is large and face up to real minimizations from time to time. Okay, the intersection forms are sparse. The intersection numbers are not so big. This is the RMS size of the intersection numbers that are not 0. It's like 10 or 5 or something like that. They're not like super gigantic intersection numbers showing up here. And the Calabi-Yau, now to your question, Tom. The Calabi-Yau is large. The volume scales very roughly. I didn't want to draw a fit here because we shouldn't pay too much attention to it. But roughly it goes like H11 to the 5th. So here's H11 only going up to 100 for this plot. And here again, log base 10 of the threefold volume. So, it's like 10 to the 12 or something like that at the top end. So pretty big. And we didn't even get to 491 yet. Now for a more impactful statement about, yes, please.
That was the minimum volume.
That's right. That's the smallest it can be without violating the stretched Kähler cone condition. So you could certainly make it the volume smaller, but then you would have to somehow argue that you could deal with some number of curves being smaller than size alpha prime. Which, I could imagine such an argument, but it would be a little challenging to imagine claiming control of the effective theory if many such curves are small. So that's the spirit in which we insist. Every curve has to be volume at least alpha prime, and then you get to this lower bound on the volume. So the volume grows pretty steeply. Now the volume infects everything. All the computations of decay constants and couplings have volumes in them. And so this says that many of the scales showing up in the theory get lower and lower as H11 grows. Now, the divisors. So suppose you got a basis of divisors, and let's evaluate their volumes, again, at the minimal place they can be, at the apex of the stretched Kähler cone, the tip of the pink cone. And let's say their volumes, let's order them. Tau 1 is less than tau 2 is less than, let's call the last one tau last. So that's the biggest one in this basis. Now, let me recompute this for some other basis. And again, find the ordered list tau 1 through tau last for that new basis. And now do this for all possible bases and find the basis that minimizes the value of tau last. That's an optimal choice for what I'm about to say. Then, this is a plot of the result. So here, H11 up to 80 now in the log base 10 of tau last. And we see that at least in every basis for H4, at least one element of the basis is this big. And this is 10 to the 4 or something like that. I'm working in conventions where the instant-on action is 2 pi times tau. So now we're talking about instant-on actions like 2 pi times 10 to the 4. So clearly negligible masses for any fields that get mass only from those instantons. So the lesson is that some axions are ultralight. Here's a plot of the actual computation of the minimum axion mass, by which I mean the mass of the lightest axion. I switched to natural log, but now it goes down to minus 600. And here's tau last. And this line here is a fit to e to the minus 2 pi tau last. So you see there's a very clearly defined edge there. So the axions are always lighter than this value. So you always have an axion that's lighter than e to the minus 2 pi times tau last. You may say, wait a minute, this seems like too simple a formula. There should be lots of stuff from the Kähler metric and e to the k and all that. Yeah, that's pretty negligible when this is so big. But that's what goes into the actual computation giving the dots. I just don't want to show the formula. And so now back to the previous plot, but we're going to superpose something on it. This line is 10 to the minus 120 m Planck to the 4th, which is to say an axion whose mass right now is h0, the present-day Hubble constant. So this is an axion that can't contribute to dark matter and can at most contribute to dark energy. The way you're supposed to read this plot is any blue dot above the red line corresponds to a Calabi-Yau threefold that cannot help but have an axion whose mass is at the dark energy scale or lighter if the alpha prime expansion is under control. So for any threefold associated with a point above the red line, either you have to violate the alpha prime expansion in the way that I described it, or you have to tolerate an axion that's ultralight, not in the fuzzy dark matter range like 10 to the minus 22 eV, really 10 to the minus 33 eV, or far, far below that indeed, even like a 10 to the minus 1,000 eV or something like that. But might as well call it zero mass. If they were scalars, absolutely, but they're not. Since they're pseudoscalars, we're saved, right? I haven't been able to argue, nor should I try to argue that the saxions are this light. The saxions can perfectly well get mass from perturbative corrections to the Kähler potential, which I am certainly not competent to compute, but I don't see any reason to expect that the Kähler potential contributions would give masses for saxions that are this small. So we're free of fifth forces, and as far as I know, these are more or less innocuous, although I'll say more things about them in a minute. Okay, so 2 more pictures, and then let's talk about implications. Here are the eigenvalues of the Kähler metric. I'm not going to call them the decay constants, because there's some ambiguities in figuring out what you define a decay constant to be. But these are just, take the Kähler metric and compute its eigenvalues. If you like, you should think of these eigenvalues as f squared, right? Because the eigenvalues of the Kähler metric have mass dimension 2 in these conventions. This is log base 10, and so this is f of 10 to the minus 6 m Planck. So 10 to the 12 GeV. So this is a phenomenologically interesting range, for example, for a QCD axion or something like that. And what you see are the histograms for the minimum, the median, and the maximum for each of the threefolds that we studied in some small test set. This is just to give you a sense of how spread out they are. Well, they're spread out pretty far, from like 10 to the minus 9 m Planck in F to 10 to the minus 3 m Planck.
How big did your volumes get again?
10 to the 12, 10 to the 14.
Up there, you're all in a regime where the spin scale is way beneath the gut scale.
Yes, yes it is. However, it's not at TeV or anything close to that. It's just below, yes, just comfortably below the gut scale.
Do you remember what kind of cut you'd have to put on H11 in order for the volume to not be bigger than 10 to the 4 or whatever, in order for the string scale to be comparable to the gut scale? Maybe we could just figure it out.
20? Yeah. You missed most of them that way. Now, one more correlation. There's a strong correlation between the smallest eigenvalue of the Kähler metric, namely the axion with the smallest f, and how big the volume is. And so you can here's the log of the volume, and here's the log of the smallest of the eigenvalues of the Kähler metric. So if you wanted to make an axion with a small f, this tells you exactly how big you need to make the volume to do it. You need to make it big. Not quite as big as in your work with Sverchek in different kinds of examples. Here we can get to the phenomenologically interesting range of decay constants with very slightly more modest values of the volume. Okay, so you have to choose. You have to either accept alpha prime corrections, accept massless axions, or work at small h11. This makes it difficult to imagine that stabilization by non-perturbative effects will be possible at large h11. And as I mentioned, many couplings are controlled by V, so you could try and search our data for outliers that have small values of the volume, and that would be where things like super Planckian decay constants would be living if they live in this ensemble at all. So now onto the cosmological implications before briefly mentioning connections to weak gravity. This, you might call it Kreuzer-Skarke Axiverse, contains many axions. Some of them are essentially massless, and they have small periodicities, at least compared to the Gott or Planck scale. There certainly could be constraints from standard model couplings of these things. A lot of people have put effort, theoretical and experimental, into this. But you have to specify the realization of the standard model. And we're not in a position to do that in a useful way yet. Something for future work, but I don't even have any particularly compelling ideas for how to do it. Now, there could also be constraints from moduli decays to dark radiation or from overproducing axion dark matter. You still have to specify the non-thermal history or the thermal history. You have to have an inflaton candidate and know what the couplings are. There's nice work on this recently by Halverson, Long, Nelson, and Carifio. But it's still an emerging subject. Now, another interesting one which doesn't require any assumptions about the history is to study constraints from black hole superradiance. In the range approximately 10 to the minus 10 electron volts, 10 to the minus 20 electron volts, with a little gap in there, there exist reasonable constraints from known populations of black holes. Regardless of whether these axion fields are populated at all, just them being present in the Lagrangian allows them to spin down black holes in certain ranges, and you could try and derive constraints. Now, this is something that we're very interested in, we're working on. The trouble is the existing work, due to, for example, Stott and Marsh, works in a particular regime where the decay constants are at least 10 to the 16. That's a nice regime because self-interactions of the axion don't matter, and the condensate that causes superradiance develops with minimal self-interactions. It's an easy analysis as such things go. All of our axions that are superradiant have much smaller f, and so they have quartic self-interactions and beyond. And so one has to go quite a ways beyond previous work, which we're gradually moving toward. Yes.
Around 10 of the 10,
Yeah.
then you do have to worry about fifth forces once there's CP violations, which of course happens. I mean, there's no.
Okay, good point.
You can't make things pseudo. There's no difference between pseudo and scale.
Okay, great. We should think about that. We haven't checked that one. Good. So finally, as a closing set of points, let me briefly describe the connections to weak gravity. So. Weak gravity conjecture for a single axion, appropriately interpreted, says there should exist an axion whose action, an instanton whose action is less than order 1 times m Planck over f. And there are some observations along these lines in the work of Banks et al. And by Sverchek as well, not quite from the context of weak gravity, but related kinds of observations. Now, for multiple axions, a reasonable thing to do is to say, suppose you've got this is the space of possible axion charges, and sigma is a vector in that space. So this is a vector of axion charge. Then a reasonable constraint would be, a version of this constraint, is there should exist an instanton whose action is less than an order 1 number times, well, the generalization of m Planck over f. And the generalization of m Planck over f is this particular Pythagorean object where I've used the metric on Kähler moduli space, inverted because this is a 1 over f. This is the sort of natural invariant generalization. There are nice discussions of this in work by Heidenreich, Ries, Fidelius, for example. Okay, so suppose we examine that constraint. In our ensemble, actually, if the vector of axion charges, so if the cohomology class associated, well, the homology class associated with this thing is in the effective cone, namely, if sigma can be realized by a holomorphic divisor, then actually, we've proved, it's an easy proof, that there exists an S with action less than pi root 3 times this. So holomorphic cycles, Euclidean D3 bands on holomorphic cycles obey the weak gravity conjecture in this formulation. You might ask, what about non-holomorphic cycles? And this brings us to another question, and really the sort of interesting shadow hovering over this work, something which leads the way to future things. We've shown that requiring that no holomorphic cycle is small implies that some holomorphic cycles are large. Because remember, everywhere I was using the Kähler form. I was integrating the Kähler form over curves, the Kähler form over divisors, etc. Well, fine. You know, the conclusion that some holomorphic cycles are very large does tell us correctly about the instanton contributions to the superpotential. But what about instanton contributions to the Kähler potential from Euclidean branes wrapping non-holomorphic cycles? And, well, we would claim only if the sublattice weak gravity conjecture is not true. And, okay, so where does that answer come from? Well, we give examples where if you assume the weak gravity conjecture is true, then this implies what, to the best of my knowledge, are new results in the theory of minimal surfaces, although I await correction by experts on that. Namely, the weak gravity conjecture appears to require the existence of small non-holomorphic cycles that are smaller than you would have thought from general reasoning about minimal surfaces, although not, I would say, smaller than you would have thought from general physics reasoning. So a quick sketch of how this goes. Let X be a compact Kähler manifold and consider some homology class, sigma 2k, where 2k is less than the real dimension of X. Now, if the class sigma has a representative regular sigma that's holomorphic, then it's calibrated by the Kähler form and it's absolutely volume minimizing in its class. And if you specify a point inside the Kähler cone, you've said what J is, and you directly determine the size of the corresponding superpotential term. But what if instead I ask a question about a class that doesn't have any holomorphic representative, that is to say a class outside the cone of effective curves or effective divisors? We'd like to understand the size of D-brane instantons wrapping such things. And this relates to an interesting old problem, more than 100 years old, Plateau's problem, which asks the question, if I give you a smooth curve in R3, what's the least area surface that bounds that? Which is the question if you dip a wire in soap, what shape bubble do you get? And the lesson from this subject was that carrying out the minimization implied by the word least within the class of smooth submanifolds doesn't always give you a limit in the class of smooth submanifolds. Sometimes you have to examine singular configurations. So there's a richly developed theory of this stuff. Worked out in the 60s by Federer and Fleming and Almgren. And basically, they've cleaned up the whole subject for use by outsiders in the sense that they defined objects that behave the way you would want. They've defined formal sums of submanifolds allowing for certain appropriately mild singularities. And what they've shown is that the minimization problem makes sense over these objects. Namely, if you let M be a Riemannian manifold of dimension n and fix a metric on it, then they prove that for any homology class you pick, in HP with p between 0 and n, there exists an area minimizing integral current. And what we've been able to do is find examples of Calabi-Yau threefolds where if the weak gravity conjecture is true, then these area minimizing integral currents that are guaranteed to exist need to be, in a certain sense, quite small. So as an indication of that, suppose X is a threefold and I have two effective curve classes. Then since the curve classes are both effective, their minimizers are holomorphic curves. Let me denote them by sigma 1h and sigma 2h. And they have some volumes. And we'd like to ask the question, is the minimizer the minimum volume representative of the difference of these two curves given by simply the difference of these two holomorphic representatives? In that case, the minimum volume of the difference of the two classes is the sum of the volumes of the two constituents. In other words, can you take a general homology class and represent it by calibrated and wrong orientation calibrated objects? In other words, can you take any curve class and represent it by holomorphic and anti-holomorphic curves and use that to compute the volume? And the answer is no, you can't. Sometimes the real thing is just smaller. the full thing is just smaller than the sums of the holomorphic and anti-holomorphic constituents. That's been demonstrated directly in a K3 surface. And cartoonishly, if this is alpha 1 and this is minus alpha 2, so this is holomorphic and this is anti-holomorphic, they combine to form something that develops a little neck where they meet. And the purple thing is a little smaller than the red thing plus the blue thing.
This is an example that does satisfy weak gravity?
It doesn't. To the best of my, well, we haven't worked it out fully here, but let's see. Let me not take a position on whether it does or doesn't. It does not show large recombination. It shows infinitesimally small degree of recombination. If you're epsilon away from an orbifold limit, then the difference of the left-hand side volume and the right-hand side volumes is just order epsilon. So very little energy is gained by fusing the BPS and anti-BPS things to form a non-BPS thing. There are directions in charge space that are far enough away from being BPS that won't do. What I haven't checked is whether this particular example has the property that this direction that I've chosen is far enough away from BPS. Okay, but we've found examples that are. So the physics of this is just that we're asking, what are the actions of non-BPS objects? They're not given by adding up the actions of a BPS object and an anti-BPS object that sum to have the same charge. You know, these things bind, they release energy. The question is how much binding there is. Well, we at least have not found any examples of finite amounts of recombination in Calabi-Yau manifolds anywhere in the literature on geometric measure theory. When recombination occurs and it's sizable, then the most important effects in the low energy EFT come from non-BPS instantons, not BPS and anti-BPS ones. And that tells you should really be worried whenever this happens. You should be very scared of trying to use holomorphic stuff, calibrated stuff, to assess how well controlled the sigma model expansion is. That's why I think this is an interesting thing. It's telling us when we ought to be more worried than we typically are about using holomorphic stuff as sort of a leading approximation to the data of the theory. So we find explicit examples in which either the sublattice weak gravity conjecture is false or else large recombination occurs. So this is my last actual slide, just a picture of our cartoon. We find cases where we find divisors, holomorphic and anti-holomorphic respectively, such that we can study a regime of parameters where it just has to be that the representative of D4 minus D6 is really small compared to D4 or D6. In other words, a huge amount of, most of the energy was lost as binding energy. And these things are very substantially bound. It doesn't seem so implausible. Yes?
Are D4 and D6 the dimensions?
No, sorry, D4, those are just the, I'm sorry, I should have changed my subscript. These are just notations for particular, this is, blue is a particular effective divisor. D6 is another effective divisor. And so D4 minus D6, the way I've constructed it, is neither effective nor anti-effective. So there's a general minimization problem not given by calibrations to determine how big is D4 minus D6. And the picture indicates that it's a lot smaller than either of the two. Yeah. Okay, so there's a potential here for a useful interaction between quantum gravity reasoning and geometric measure theory, perhaps, and more generally for thinking about minimal surfaces. So let me conclude. I described the construction and partial study of a landscape of some millions of Calabi-Yau threefold hypersurfaces. And in getting there, we made improvements by many orders of magnitude on most of the key measures of difficulty in the computation, and we can easily access all of Kreuzer-Skarke. This is a step toward our goal, which is to construct a large ensemble of cosmologically realistic solutions by stabilizing moduli in these geometries. We can use this to test ideas about quantum gravity EFTs. And one of the things that we find is when the curvature expansion is under control, many cycles are very large, the volume is very large, and some axions are massless. And the root cause of that is the narrowness of the Kähler cones. So there are tons of directions for the future. One really ought to feed into this information about the non-perturbative superpotential, about the non-perturbative Kähler potential, figure out which threefolds really dominate, carry out a survey weighted by which ones dominate, and then actually understand these limits that I just hinted at. And finally, you might try to search for unusual exotic geometries that have nice desirable properties like large field ranges or something like that. And finally, overall, what we aim to do in the coming years is to develop this ensemble and extensions of it into a precise testing ground for ideas about quantum gravity in 4 dimensions. Thank you.